Well, in this lecture, you would find the remaining topics related to shear strength of soils. Uh, we will discuss unconfined compression test, then a few comments on the triaxial test, then the determination of pore water pressure during undrained loading, analysis of pore water pressure, vein shear test, stress path, and then you would find few solved examples or problems, and then the shear strength of partially saturated soil. This topic will be discussed, and at the end you would find some information about the environmental geomechanics. So here you can see the description given related to the unconfined compression test. On this slide, you would find the comments on triaxial test. Three types of strength parameters: consolidated drained, consolidated undrained, and unconsolidated undrained were introduced. Their use depends on drainage conditions. Consolidated drain strength parameters can be used to determine the long-term stability of structures such as earth embankments and cut slopes. Consolidated undrained shear strength parameters can be used to study stability problems relating to cases where the soil initially is fully consolidated and then there is a rapid loading. An excellent example of this is the stability of slopes of earth dams after rapid drawdown. The unconsolidated undrained shear strength of clays can be used to evaluate the end of construction stability of saturated cohesive soils with the assumption that the load caused by construction has been applied rapidly and there has been little time for drainage to take place. The bearing capacity of foundations on soft saturated clays and the stability of the base of embankments on soft clays are examples of this condition. Determination of pore water pressure during undrained loading. We can determine pore water pressure U for the case of hydrostatic loading and steady-state seepage. We can evaluate U in the case of consolidation, that is drained loading. It is often necessary in engineering practice to be able to estimate just how much excess pore water pressure develops in undrained loading due to a given set of stress changes. Now I need your attention. This is very important point. Consider what happens when we apply the hydrostatic cell pressure sigma c and prevent any drainage from occurring. If the soil is 100% saturated, then we obtain a change in pore pressure delta U numerically equal to the change in cell pressure delta sigma sub c we just applied. In other words, the ratio delta U over delta sigma c equals 1. So after application of cell pressure, B is equal to U sub c over sigma 3. Shear, corresponding to shear, A bar is equal to delta U sub D over delta sigma d. This is the increase or change in pore water pressure due to change in deviator stress. And this is the change in the deviator stress. And at failure, A bar, it can be written as A bar sub F, that is delta U sub D sub F divided by delta sigma D sub F. So U is equal to U sub C plus delta U sub D. Now from this you can see that U sub C is equal to B into sigma 3. So we have written B into sigma 3 over here. Now from this concept you can see that A bar multiplied by delta sigma D is equal to delta U D. So this delta U sub D, it has been replaced by A bar times delta sigma D. And keep this thing in the mind that A bar is equal to B multiplied by A. If we just uh, write this equation like this, that B sigma 3 plus A bar into sigma 1 minus sigma 3, that is the deviator stress. And for the case of full saturation, this B, the pore water pressure factor, that is equal to 1. So this equation can be written like this, replacing A bar by B into A. Ultimately, you are getting this formula, that is U is equal to sigma 3 plus capital A into deviator stress sigma 1 minus sigma 3. So let us consider the case of UU test. Step 1, immediately after sampling, no vertical stress, no lateral stress. Step 2, after application of hydrostatic self-pressure, that is sigma C, that is equal to sigma 3, and it is acting all around the sample. So this is vertical stress is also equal to sigma C, that is sigma 3 initially. And the pore water pressure, that is delta sub U sub C, that is because of this hydrostatic self-pressure. So you can see this thing that delta U sub C is equal to B into delta sigma 3. So this one is increase of pore water pressure due to increase of cell pressure. This is increase of cell pressure, and this B is the Skempton pore water pressure parameter. So this B is in fact the function of saturation. For saturated soils, B is nearly equal to 1. So if soil is fully saturated, then B is equal to 1. Hence, delta U sub C is equal to delta sigma 3. Step 3, during application of axial load, that means deviator stresses are being induced. So sigma 3 plus delta sigma D over here, sigma 3, and here now you are having the pore water pressure change, that is delta U sub C plus minus delta U sub D. And now again look at this equation, delta U sub D is equal to A bar into delta sigma D, whereas this one delta U sub D, that is the increase of pore water pressure due to increase of deviator stress. This one is increase of deviator stress, and this A bar is the Skempton pore water pressure parameter. Now combining steps 2 and 3, we can write delta U sub C is equal to B into delta sigma 3, and delta U sub D is equal to A bar into delta sigma D. Total pore water pressure increment at any stage, delta U is equal to delta U sub C plus delta U sub D. So here you can write the expressions, and ultimately you are getting this formula. and then you can replace this delta sigma d by delta sigma 1 minus delta sigma 3, so you can write this equation in this form. Now this particular equation can also be expressed as this, and we have simply considered this thing that A bar is equal to B into A, so we can write this equation like that. This is the well-known Skempton pore water pressure equation for relating the induced pore pressure to the changes in total stress in undrained loading. For saturated soils, B is equal to 1. The above mentioned equation can be transformed into this. So this is the equation ultimately you are getting. Now, if you just look at the important points related to the pore water pressure parameter, so one by one we will go through all these points. The pore pressure parameter capital B expresses the increase in pore water pressure in undrained loading due to the increase in hydrostatic or cell pressure. If the soil were less than 100% saturated, then the ratio of the induced delta U to the increase in cell pressure delta sigma C would be less than 1. The parameter capital B is very useful in the triaxial testing to determine if test specimen is saturated. The Skempton's pore water pressure parameter capital A is a measure of how much pore pressure will change during shear phase. Like the parameter B, the parameter A also is not constant. It is very dependent on OCR, over consolidation ratio, and entropy, sample disturbance. The parameter A can be calculated for the stress conditions at any strain up to failure as well as at failure. The Skempton pore pressure coefficients are most useful in engineering practice since they enable us to predict the induced pore pressure if we know or can estimate the change in the total stresses. Typical examples are in the design and construction of highway embankments and compacted earthfill dams. Now here you can see the variation in capital B with the degree of saturation, and you can see that when degree of saturation is 100, its value is nearly equal to 1. And look at the A sub F bar value, and you can see that with the increase of OCR, its value is decreasing. The general range of values of A bar F in most clay soils is as follows. Normally consolidated clays 0.5 to 1, and over consolidated clays minus 0.5 to 0. Now in this slide you would find some information about the vane shear test. You can go through this slide yourself and you could be able to get a real feel about the vane shear test very easily. Now we have reached this topic, the stress path. That is very, very important. States of stress at a point in equilibrium can be represented by a Mohr circle in a tau sigma coordinate system. Sometimes it is convenient to represent that state of stress by a stress point which has the coordinates P dash and Q dash. So sigma 1 dash plus sigma 3 dash over 2, and Q dash is equal to sigma 1 dash minus sigma 3 over 2. Now if you just look at that one, if we are considering the total stress, So you can see that this point is having the coordinate sigma 1 minus sigma 3 over 2, this one, and this coordinate is sigma 1 plus sigma 3 over 2. But when you are having the effective stress Mohr circle, so in that particular case it would be sigma 1 dash minus sigma 3 dash over 2, and this would be sigma 1 dash plus sigma 3 dash over 2. So this particular point, which is having the coordinates P dash and Q dash, or P or Q, that is called as the stress path. Stress point rather, you can say. So we often want to show successive states of stress which a test specimen or a typical element in the field undergoes during loading or unloading. So both loading and the unloading case. A simple case to illustrate stress paths is a common triaxial test in which sigma 3 remains fixed as we increase sigma 1. So you can see that sigma 3 is fixed, but we are increasing sigma 1. So this is sigma 1 over here. Here sigma 1 is this one, and here the sigma 1 is this one. So in this way, we are getting these points. And this is basically tau versus sigma plot, and here Q versus QP. And if you just consider these points, so this is the plane of maximum shear. There might be a confusion, especially if the stress paths were complicated. Therefore, it is simpler to show only the locus of the stress points, as you can see over here. This locus is called the stress path, and it is plotted on what we call a PQ diagram. A stress path is therefore a line that connects a series of points, each of which represents a successive stress state experienced by a soil specimen during the progress of test. So this point is very, very important, and I would like to repeat it. A stress path is therefore a line that connects a series of points, each of which represents a successive stress state experienced by a soil specimen during the progress of a test. Both P and Q could be defined either in terms of total stresses or effective stresses. Now here you can see this one, the failure envelope, and if you just look at this one, the dotted line, this is a modified failure envelope, and you can see that this angle is equal to alpha. The straight line ID, here look for this one, is referred to as the stress path in a Q versus P plot for a consolidated drain triaxial test. And here you can see again, this was the failure envelope, and if you just consider this point and just draw this line, so you can see that this modified envelope is making an angle of alpha. So Mohr-Coulomb failure envelope in terms of stress invariants. And here you can see the stress path, this one. So stress path plot of Q dash against P dash for a consolidated undrained triaxial test on a normally consolidated clay. Mohr's failure envelope is generally obtained by drawing a common tangent to Mohr circles at failure, as you can see the figure. This method of obtaining the failure envelope is not convenient, as it becomes difficult to draw the required tangent touching all the circles. A modified failure envelope as explained below is more convenient. A modified failure envelope is a plot between P and Q values of failure. And you can see here Q, that is sigma 1 minus sigma 3 over 2. If you are considering the effective stresses, obviously sigma 1 dash minus sigma 3 dash over 2. And here sigma 1 dash plus sigma 3 dash over 2, and that is P. So in this way, when you are having these points, you can join the points, and this way you are having this modified envelope, and this angle with the horizontal is alpha. There are basically three types of stress paths. Number one, effective stress path, ESP. Number two, total stress path, TSP. And number three, total stress minus static core pressure path, TSSP. So first look at the effective stress path, ESP. It is plotted between effective stresses sigma 1 dash plus sigma 3 dash over 2 and sigma 1 dash minus sigma 3 dash over 2. Total stress path TSP, it is plotted between total stresses sigma 1 plus sigma 3 over 2 and sigma 1 minus sigma 3 over 2. And as far as the total stress minus static core pressure path TSSP is concerned, it's the plot between sigma 1 plus sigma 3 over 2 minus u and sigma 1 minus sigma 3 over 2, where U sub s is the static core water pressure. Well, it may be noted that the vertical axis for all the stress paths is the same as sigma 1 minus sigma 3 over 2 or sigma 1 dash over sigma, I will repeat, sigma 1 minus sigma 3 over 2 is equal to sigma 1 dash minus sigma 3 dash over 2, and that is equal to Q. If the principal planes are horizontal and vertical, the vertical stress sigma V and horizontal stress sigma H are the principal stresses. In that case, the above three basic stress paths can be drawn between sigma V dash plus sigma H dash over 2 and sigma V dash minus sigma H dash over 2, sigma V plus sigma H over 2 and sigma V minus sigma H over 2, and here sigma V plus sigma H over 2 minus U sub S and sigma V minus sigma H over 2 respectively. In the normal triaxial test, as the static pore water pressure U sub S is 0, the stress paths 2 and 3 coincide. However, if a back pressure is used in testing, the two stress paths will be different. In field, the static pore water pressure depends upon the position of the water table with respect to the point. So now look at these three figures, A, B, and C. So we are going to consider different stress paths. So figure A shows the stress path for a drain test. The point A corresponds to the stress condition when only the confining pressure acts on the specimen, as sigma 1 is equal to sigma 3 and P is equal to 0. The point F represents the failure, this one. Figure B shows the stress path for a consolidated undrained test on a normally consolidated clay, and figure C on an over-consolidated clay. Okay, figure 13.39, you would be able to see it on the next slide, shows the effective stress path A is equal to 1 for conventional triaxial compression test where the sigma h is equal to constant, that is delta sigma v is positive and delta sigma h is equal to 0. The typical example is the case of footing subjected to vertical loads only. So this is the figure. The stress path A2, well, if you just look at the stress path A2 over here, this one, is for the unloading case when delta sigma h is negative and delta sigma v is equal to 0. The typical example is the case of active earth pressure on the retaining walls. The stress path A4, look at that, A4. The stress path A4 is for the loading case in extension test when delta sigma v is equal to 0 and delta sigma h is positive. It represents the passive earth pressure case. The stress path A3, this one, is for the unloading case in the extension test when delta sigma h is equal to 0 and delta sigma v is negative. It represents the case of the foundation excavation. This slide is very important. The following points about the stress path are worth noting. Number 1, a negative value of Q indicates that the horizontal stress is greater than the vertical stress, and a positive value that the vertical stress is greater than horizontal. Number 2, TSP, TSP total stress path to the right of ESP, effective stress path. So TSP to the right of ESP indicates a positive pore water pressure, and TSP to the left of ESP a negative pore water pressure. And here TSSP, TSSP, the total stress minus static pore pressure path to the right of ESP indicates a positive excess pore pressure, and TSSP to the left of ESP a negative excess pressure. When both coincides, excess pore pressure is 0. So these are the very, very important points. Then you would find the problem related to the stress path. You can go through this problem yourself. So another example related to the triaxial test. And then some information is provided regarding the triaxial shear test device, and the UU test has been prepared with the unconfined compression test. Okay, this topic, that is the shear strength of partially saturated soil, is also very important. The effective stress in a partially saturated soil is determined using Bishop's equation. Sigma bar or sigma dash is equal to sigma minus u sub a minus psi. This symbol is pronounced as psi into u sub w minus u sub a. So this u sub a is a new thing for you, that is the pressure in gas and vapor phase, or simply you can say the pore air pressure. U sub W is not a new thing for you. This is simply the pore water pressure. So psi is a factor which is being considered for the unsaturated condition. And again here U sub A, that is the pressure in gas and vapor phase, or simply you can say the pore air pressure, and this is the stress, the total stress. The parameter psi depends upon the degree of saturation. As it is difficult to determine accurately the effective stresses in partially saturated soil, it is common practice to draw the failure envelope in terms of total stresses. Unconsolidated, undrained triaxial tests are conducted on a number of samples with a given degree of initial saturation. The Mohr circle in terms of total stresses are drawn at failure and the failure envelope obtained. As you can see in the figure, as an increase in the confining pressure causes an increase in the solubility of air in the voids, the degree of saturation increases and the failure envelope leads to the horizontal. For design purposes, the curved envelope is approximated as a straight line. Well, if we consider this thing U sub W minus U sub A, there is one term that you would find in the literature, that is the metric suction. That is in fact U sub A minus U sub W. I will repeat, U sub A minus U sub W, that is also called as metric suction. Okay, the shear strength, that is C sub U plus sigma tangent U sub S. So S is the shear strength, C is the cohesion intercept, and phi is the angle of shearing resistance. As it is difficult to draw the correct failure envelope, the values obtained are necessarily approximate. This point is very important. As the initial degree of saturation is increased, the shear stress to cause failure is decreased. I will repeat this thing. As the initial degree of saturation is increased, the shear stress to cause failure is decreased. For a fully saturated soil, the total stress failure envelope is horizontal, as already discussed for fully saturated soils. The tests are conducted simulating the field conditions. However, an actual soil deposit in field may not remain unsaturated if it has an access to water. For such a case, the soil sample is saturated in the laboratory and the undrained shear strength in saturated conditions should be determined. So you can see here shear stress versus sigma plots, and you can see that failure envelopes. So as the degree of saturation is increasing, your failure envelope is coming in the downward direction. So showing this thing that the shear strength is going to decrease with the increase of degree of saturation. Partially saturated soils are encountered in the field in artificial fills or residual soils. A compacted soil is ordinarily placed at optimum water content and it is therefore partially saturated. Its behavior depends upon the amount of air present in the pore space. If the volume of air is relatively small, the soil may get saturated under stresses. If the air content is very large, the soil remains unsaturated and undergoes large volume changes even in undrained conditions. The shear strength of partially saturated soils is not yet fully understood. It is still in active research stage. Now, from these slides onwards, you would find some information about the environmental geomechanics. A recent development in geotechnical engineering, environmental geomechanics, as the word of environmental is portraying something. So I will cover this topic very briefly, but you can go through all these slides yourself. These slides are self-explanatory. So I will switch over to the main topic, environmental geomechanics. So first, to develop some field, you would find such type of slides which are given in the beginning of this article. So look at the scope of environmental geomechanics. Assessment of pollutant being discharged on the soil deposits, process by which the pollutants travel in geo-environment, protection of groundwater aquifers from contamination, methods of cleaning the contaminated sites, methods of creating value-added products. These are the, you can say, the points which are highlighting the scope of the environmental geomechanics. So the specific studies on the hazardous waste, physical, chemical, mineralogical, electrical and thermal characterization, geoenvironmental hazards, natural and man-made, recycle and reuse of industrial waste, the role of geotechnical engineering in environmental protection, surface and subsurface contamination, characterization of contaminated ground, geoenvironmental site investigation, site assessment technologies. So here the soil-water environment interaction has been explained. The natural environment, man-made environment, and the components have been highlighted on this slide. Here the soil response to environment, and here the basic concepts of analysis. So let's talk about the scope of geo-environmental engineering. Any project that deals with the interrelationship among environment, ground surface, and subsurface, that soil, rock, and groundwater, falls under the purview of geoenvironmental engineering. Here the purview means the scope of geoenvironmental engineering. The scope is vast and requires the knowledge of different branches of engineering and science put together to solve the multidisciplinary problems. A geoenvironmental engineer should work in an open domain of knowledge and should be willing to use any concepts of engineering and science to effectively solve the problem at hand. The most challenging aspect is to identify the unconventional nature of the problem, which may have its bearing on multiple factors. For example, an underground pipe leakage may not be due to faulty construction of the pipe, but caused due to highly corrosive soil surrounding it. The reason for high corrosiveness may be attributed to single or multiple man-made factors which need to be clearly identified for the holistic solution of the problem. The conventional approach of assessing the material strength of the pipe alone will not solve the problem at hand. A lot of emphasis has been laid for achieving a green environment. Despite a lot of effort, it is very difficult to cut off the harmful effects of pollutants disposed of into geoenvironment. The damage has already been done to the subsurface and groundwater resources. An effective waste containment system is one of the solutions to this problem. However, such a project has different socio-economic and technical perspectives. The realization of such projects requires the contribution of environmentalists, remote sensing experts, decision makers, common public during its planning stage, hydrologists, geotechnical engineers for its execution stage, and several experts for management and monitoring of the project. The totality of the problem can be visualized under the umbrella of geoenvironmental engineering. Therefore, the real challenge for geoenvironmental engineer is how well he can integrate the multidisciplinary knowledge for achieving an efficient waste containment. As mentioned earlier, in most parts of the world, damage has already been done to the geoenvironment and groundwater reserves due to indiscriminate disposal of industrial and other hazardous waste. Owing to the excessive demand, it becomes important to remediate and revive the already polluted geoenvironment and groundwater. A geoenvironmental engineer has a great role to play for deciding the scheme of such remediation practice. A lot of concepts from soil physics, soil chemistry, soil biology, multi-phase flow, material science, and mathematical modeling need to be taken for planning and execution of an efficient remediation strategy. Therefore, it is essential for the geo-environmental engineer to think out of the box to an extent that the knowledge can help him visualize the problem better and suggest efficient solution. Else, the solution to such problems becomes a trial and error process, or rather, learn from mistakes and rectify. Since such projects are cost intensive, one cannot afford to take too much of chances. Another important issue is the reuse and recycling of waste materials, which reduces the burden on our environment manifold. A very good example is exploring the possibility of mass utilization of fly ash for geotechnical applications. However, while using waste materials for meaningful application, there are issues such as short-term and long-term impact, which is a governing factor for deciding its selection as a viable material. Although short-term behavior can be assessed using planned laboratory evaluation, it often becomes difficult and complex for understanding the long-term behavior. The scope of geoenvironmental engineering is to simplify the process of understanding the behavior and resort to reliable predictions and estimation. This would require a thorough knowledge on material science and chemistry and the reaction it undergoes with time. This is indeed a tough task, but needless to say, such challenge makes this subject quite interesting. The frequent occurrence of landslides, especially during rainy season, has drawn the attention of researchers and practicing engineers. The conventional slope stability analysis is partially helpful in understanding the problem. A wider perspective of the problem would be to include factors such as infiltration and seepage of rainwater through the slope. Such factors are going to add on to the instability of slope. The scope and challenge for the geoenvironmental engineer is to couple the geotechnical, geological, and hydrologic concepts to explain rainfall-induced slope failure. Construction of flood protection works such as embankments and levees also come under the purview of geoenvironmental engineering. Unless a thorough hydraulic study is conducted, any geotechnical measures for flood protection would prove to be futile. This is specifically true for large rivers and for meandering sections. So you have seen that the behavior of soil is quite complex, or it would not be wrong to say that multi-phase behavior of soil is there. Role of soil in geo-environmental application. We have already talked about that, but you would find some more information on these slides. And then at the end you would find the importance of soil physics, and the significance of the soil physics has been highlighted on these two slides. So that's all from my side. Thank you.